Yeah, so today I will be talking about work that's joint with Sinan, who's my mentor at Courant. It's based on two recent articles, like very recent. These two actually only appeared on the archive last night at around 10 p.m. We tried our very best to get these out before this talk today. And so it's going to be the first time we will be announcing these results, not only at a seminar, but also to other people. We've been quite secretive about these works. You can also find these on my webpage. So let me just start with the question we are interested in, whether it's possible to approximate any reasonable function with now a coarsely quantized neural network. Now, I'm sure everybody here has seen the definition of a neural network. It's a composition of affine maps with some nonlinearities. These A matrices are called the weight matrices, and the B vectors are called the bias vectors. This is just a regular neural network where now the entries of A and B are in general real. By a quantized network, we mean just a neural network whose non-zero parameters, and by parameters, I'm loosely referring to weights and biases, must be selected from a discrete set of values. And this is what we call an alphabet. So the most common type of alphabet, which one uses to store real numbers on a computer, is to just use a high resolution arithmetic progression. So here you should think of delta as a very small number and then m as a very large number. And as long as m is large enough, delta is small enough, you can just round, say, any real number to its nearest neighbor in A, allowing you to now digitize it. But this is not really what we're interested in. We're interested in the concept of a coarsely quantized neural network, which is one that's a quantized neural network, except that the alphabet only uses a small collection of possible values. So the most extreme case of this is you can just think of like a 1-bit alphabet, like plus or minus 1. So in this case, you could ask the question, you give me a function. Can I find just plus or minus 1s as the weights and the biases that will allow me to approximate the function you give me using a neural network? I'm allowed to use however many layers, however many weight matrices I need, but the requirement is that every non-zero entry is only plus or minus 1. Okay, it's not an obvious question, but before I get into the math, let me just motivate why we even asked this question in the first place. The first is a practical issue, which is that it seems like every year, these neural networks are getting bigger and bigger. Seems like to get better performance, you just need bigger networks, which means more layers, more parameters, more cost of storage, more costs to even perform a forward operation. Well, we don't want to only use these networks on these state-of-the-art computational machines. I mean, eventually we would want to port these onto phones or cars. And these things are clearly of interest because if you can have a network on a phone, then this will, completely change the way in which people live their lives. So one way of approaching this problem is through quantization. There's this survey article that I've referenced here that's mainly written from the perspective of engineers. And the entire premise is that if you can quantize the network, in other words, you can find a low bit representation. So take every weight, every bias, create a low bit representation of it, then that low bit representation is not only cheaper to store, which is not really an issue, like most phones have large memory capabilities, but the main gain is really faster forward pass. So it'll be cheaper to evaluate the network on a new object. And this means that not only is it faster, but it requires less energy consumption. So you could imagine having some network that would do image recognition on your phone, and maybe there's some hope of doing this in real time. But the mathematical community, especially perhaps members of this audience today, have developed more sophisticated quantization methods. So for example, Rayanne and Alex Powell, they have recent works on applying these more sophisticated techniques towards this problem. But this is like a very open and new direction. Our second motivation is more conceptual. So these networks contain way more parameters than probably necessary, which means that they are over-parameterized. For a given function, you can usually find several sets of parameters that will represent that fixed function. So in other words, if we define P of F as the set of parameters that whose neural networks with these parameters will generate this fixed function, if we just imagine it as a curve in this extremely high dimensional parameter space, then this question about quantization, which means that I want to, instead of using a real value for every one of these parameters, I want to use a discrete value, is really a question about whether I can find some lattice in this high dimensional space for which every single one of these parameter curves intersects or gets very close to one of these lattice points. And so the question really is, how few lattice points do I need? So can I come up with like a very sparse lattice such that for every single one of these parameter curves, they get very close to one of these lattice points? All right, so let me just jump into now more of the math aspect of this. So, of course, what makes this question difficult to answer? Like, there's a ton of approximation theory results for neural networks. In fact, there was already a talk on this at the FFT earlier this semester. So why is it that we can't just use these existing results to tackle this problem? So for the most part, these results employ like a common strategy. The idea is that for a fixed function, we try to approximate it by a linear combination. So the phi's here are implementable by like a neural network. So for example, like wavelets, local polynomials. And then the a's are like the coefficients, like you can think of it as like a frame coefficients of the function f. So, well, what happens? Well, if we use a high resolution quantizer, then there really is no issue. We would just follow the same steps. We get some error due to quantization, but it might not be too bad because we would be using a high resolution quantizer. Now, the problem really occurs when we start getting into coarse quantization. Because, well, how is this function implemented by a network? Typically, the network would implement each of these phi's. And then in the last layer, they would add these phi's together using this as a sum. So it would weight each of these phi's by the a's and then add them together. If we were to use a quantized network, say with only plus or minus ones, we would need to be able to implement each phi with a network with only plus or minus ones. Okay, it's already posing some issues. But then these a's themselves would also have to be plus or minus one. And so you would be asking a question about how to approximate a given function with a linear combination of plus or minus ones. And that's not a simple question to answer. So we would have to make some serious modifications to what is known in order to be able to actually address this question. So it turns out that Bernstein polynomials will be one of our main tools. And let me explain how we ended up looking at Bernstein. It's not obvious, of course. So here's kind of like our wish list for what we want to do. So again, if we want to follow the same type of strategy, we want to find a set of phi that satisfies a few nice properties. The first is that they have to be rich enough in the sense that linear combinations of these phi's can efficiently approximate large function classes. So again, like wavelets, local polynomials, these types of things. Okay. The second requirement is that they can be implemented by a coarsely quantized network. So if we removed this part in blue, this would just be your usual approximation theory question for neural networks. But now we're adding this additional constraint that they're coarsely quantized, but we also need a third constraint. And the third constraint will be that coefficients in the phi basis can be quantized in an effective way, by which we mean that if somebody presented us with a linear combination of these phis where the a's are real, then we can find a set of sigmas belonging to our alphabet such that their difference is small. We want these three requirements because this is exactly how we'll approach the analysis. We'll split the error between F and a neural network approximation into these three terms. The approximation made by linear combinations of phis, the error made by quantizing the coefficients in the phi basis, and then finally, this error due to implementation, approximating the phis with a network. Okay, so we have these three wishes, and they seem to be competing, right? Like here, this is saying, okay, we want a lot of different types of phis, but then this implementation criteria is saying that, well, no, we can only look at certain special ones that we can implement. And then this quantization criteria is further restrictive. So what can we do? So it's natural to look at the most restrictive criteria and then try to fit the more flexible pieces around the most restrictive one. And the most restrictive criteria here is the quantization one. There's actually very few results or very few positive results on approximations of this nature. Like the most famous ones would be approximation of band limited functions using sigma delta quantization. This was developed by Ingrid Dobuchis, Ron DeVore, and then further work by other members of this community. So how do we start with Bernstein? Well, let me first tell you about this result by Kantorovich. He showed that if you have a continuous real value function, okay, on the unit interval, and if f at the endpoints are integers, Kantorovich said, okay, let's define this modified Bernstein operator. So it looks a lot like your usual Bernstein operator, except now we'll round each term of this form. It's f sampled at k over n times this combinatorial factor. We round it to the nearest integer. And he showed that this modified Bernstein polynomial of f converges to f uniform. Okay, so this is already a quantization result. It's saying that we can approximate f with integer coefficients with these polynomials as the basis. Okay, so what goes wrong here? It turns out it's not helpful for us. It's a nice result because it implies that polynomials with integer coefficients are dense in the space of continuous functions. I mean, it's quite nice in that sense. But the main drawback is that if we actually look at these integers that we would need to use in this scheme, they could be extremely large. Like if f were bounded by 1, then each of these combinatorial factors, I mean, they're maximized when k is approximately n over 2, and you know, basic Stirling tells you it could be as big as 2 to the n. So if we use Kantorovich, the integers we would need are from negative 2 to the n to 2 to the n. That's an enormous set of integers. It's basically useless for coarse quantization. But it gives us hope because in the past 2 decades, there has been tremendous innovations in quantization that were just not available beforehand. So Kantorovich is using just something very simple, just rounding these guys. Let's see if we can do something more sophisticated. So here we have our usual Bernstein polynomials. We have our usual theorem by Bernstein, says that the Bernstein polynomial of f converges to f uniformly. The question is, for any continuous function in epsilon, can we find a sequence of plus and minus ones for which now, instead of using these as the coefficients in my linear combination, I only want to use plus and minus 1. Okay. Now there's a problem with this question. Well, there's 2, and this question is false for, can't be true for kind of simple reasons. The first reason is scaling. The sum of these Bernstein polynomials is always 1. So if the sigma k's are plus or minus 1, the biggest this guy could be is 1, and the smallest it could be is negative 1. So there's no hope of approximating every continuous function. But that's not an issue. It's just a scaling issue. So you could just simply say that, okay, let's say f is bounded by 1. The second issue has to do with the endpoints. So each of these Bernstein polynomials, they vanish at the endpoints except for k equals 0 and k equals n. If we look at the sum, if the sigmas are plus or minus 1, then at the endpoints, the sum can only be plus or minus 1. So there's no hope of getting a uniform bound on the entire interval. You would either have to weaken the norm or weaken the way you measure the error, or you put more restrictions on f. We decide not to put more restrictions, so we just weaken the error. So what we say is, here's the new question. For every continuous function that's bounded by 1, and for every epsilon, can you find a sufficiently large n and a sequence of plus or minus 1s, such that for all x away from the endpoints, f minus this plus and minus 1 linear combination of these Bernstein polynomials is within epsilon? And I mean, quite surprisingly, perhaps, the answer is yes. So it turns out for Lipschitz functions, we can actually give this quantitative rate. So we can find a sequence of plus and minus 1s for which for every Lipschitz continuous f, whose sup norm is bounded by 1, this error for each x is on the order of the Lipschitz constant, square root of n to k, something that depends on x. So you already see the failure of this bound at the endpoints, because when x is either 0 or 1, this upper bound is O of 1. Okay. So in comparison to Kantorovich, if we're willing to, settle with this issue of not being able to approximate at the endpoints, then we're using significantly fewer bits. We only need plus and minus 1. Kantorovich needs like minus 2 to the n to 2 to the n. This estimate doesn't look so pretty because of these x factors. So you could derive an L1 bound from this, for example. You could show that the error in L1 is on the order of the Lipschitz constant of f divided by the square root of n. Okay, so, I mean, I don't know, but from my perspective, I feel like this is a very surprising result that you can do this, because, by density, you would be able to show that on a subinterval, every continuous function can be approximated by a plus minus 1 linear combination of Bernstein polynomials. And from the mathematical quantization community, this might also be surprising for a different reason, which is that usually to do coarse quantization, one needs something called redundancy. So the simplest way I can explain this is if you think about a basis for a vector space, if you have a basis, then the coefficients of any vector in this vector space has to be unique. But if you have non-uniqueness, like a frame, then the frame coefficients are non-unique. So there's some wiggle room for you to pick certain ones. But here, the Bernstein polynomials is a basis for the space of polynomials of n plus 1. Of degree n, right? So it's an n plus 1 dimensional space. But somehow you can still do this approximation with only plus and minus 1 coefficients. So when we first had a result like this, we actually did it for the L2 norm. Our proof was very complicated, involved a lot of tedious calculations. We didn't even get that good of a bound. But after some simulations, going back and forth between simulations and proofs, we managed to distill it down to the most basic ideas. And now I can give you an almost embarrassingly easy proof of this theorem. Okay, it's so simple that any undergraduate should be able to understand this, and I can show it to you in 2 slides. So how does this work? So the plus and minus 1 sequence is chosen constructively. It's through an algorithm called first order sigma delta quantization. So first order is not hard to explain. It's only when we get into higher order sigma delta that things get complicated. But first order, one can just understand it without any background. The idea is we'll let A be the samples of F at these grid points, and then we'll find this sequence of plus and minus 1s in such a way that this difference equation is satisfied. I want A minus sigma to be this finite difference of some other sequence U. And the key here is that the system is solvable with a U that's uniformly bound. So this infinity bound on U is independent of n, which is super crucial because this will allow us to take n arbitrarily large. We can give this explicitly, but showing that this is possible is just simple induction. It's only when we get into higher order that this is not so clear. To bound the total error, I pick sigma according to this algorithm. I split the error into two terms. The first term is the usual approximation of f with its Bernstein polynomial. The second term is the Bernstein polynomial of f minus my plus and minus one linear combination. The first term, because f is Lipschitz, is bounded by the Lipschitz constant of f divided by square root of n. And for the second term, I just use the fact that A minus sigma is delta U. I just have to find the analogous bound for the second term, and we're done. And to do that, well, I just do one integration by parts. Okay, if I just make this notational convention here, that P of n with k plus 2 as the index is exactly 0, I can rewrite it as just one sum, just kind of incorporating the boundary term into one sum. It's mainly a technical simplification to make the notation simpler. But from here, it's still very basic. I just use the fact that I can bound this sum in terms of the infinity norm of U times this like quote unquote frame variation term. So a term like this was implicit in earlier works on sigma delta, including work of Dobeshees and Devore. But this term was really coined and exploited by two papers written by John, Alex, and Oscar Yilmaz, both in 2006. But from here, I just use the exact formula for this difference. Use Cauchy-Schwarz. Normally, there would be a second term that appears from Cauchy-Schwarz, but because the Bernstein polynomials form a partition of unity, that second term will be bounded by 1. And this term, there's an exact formula for it. It's the second central moment of a binomial random variable. And so I get this final term here. And that's it. That is the proof that essentially every continuous function can be arbitrarily well approximated inside the unit interval by a linear combination of plus and minus 1 Bernstein polynomials. Okay, so just to show you that I'm not entirely crazy, we actually implemented this. Like I said, the sigma delta algorithm is constructive. So if we look at this function here, it's essentially a sinusoid, but truncated so it's between -1 and 1. And in this plot, we have our usual Bernstein polynomial of f, as well as the plus and minus 1 linear combination that is constructed in the theorem. You can see that the approximant doesn't do well near the endpoints. So that's as to be expected from the theorem. We can't approximate within like 1 over square root of n of the endpoints. That's fine. But you see that visually it's not bad. It's pretty good. It's comparable to your usual Bernstein polynomial of f. And for fun, you can actually write down like a binary representation of this function. So to make it look prettier, if we swap out -1 with 0, then this string of length 101 are its quantized Bernstein coefficients. So you can think of this as like a binary representation of this function up here. And essentially, by inspection from the proof, all of the magic that goes on here is when we look at these finite differences between Bernstein polynomials, there's massive cancellation. Like this entire term will be on the order of square root of n, as long as x is not too close to the endpoints. Okay, so this is how we ended up with Bernstein. So Bernstein gives us hope that these fees satisfying our wish list might actually exist. So maybe we should just use the Bernstein polynomials. But there's still a big issue when applying these to neural networks. I mean, the usual issue is high dimensionality, right? But it's more profound in our case because the cursive dimensionality is usually referred to in terms of a computational cost, like it's harder to compute, more expensive to compute in higher dimensions. But for us, it turns out to be a much bigger issue than just that. The reason here is that in higher dimensions, there's no, like sigma delta is primarily a one-dimensional tool. Like there are extensions to higher dimensions, but there's no dimension-independent alphabet that is stable for sigma delta. Why is that a problem? Well, the only advantage of sigma delta is that it allows you to do coarse quantization. Once you exceed, like, say, like 16-bit alphabet, then there's no advantage to sigma delta. You would just do regular rounding at that point. So this is a huge issue because D in all of these applications is at least like 1,000. The second issue is that in higher dimensions, one generally works with smaller function classes. I mean, we could stick with the class of Lifshitz functions, but due to the cursive dimensionality, the approximation rate would be so slow that there would almost be no point in doing that. So this essentially forces us to consider higher regularity classes. So say spaces of smooth functions. But now here's the issue, which is this usual saturation result for Bernstein. And this is also why Bernstein polynomials aren't used as often in practice. It says that, okay, if f is C2, then the rate of convergence between f and its Bernstein polynomial is on the order of 1 over n. I mean, unless the second derivative of f is 0. So unless f is like a linear function, the best rate of approximation you can get is 1 over n. F could be like 1,000 times differentiable. And this says that even if it's 1,000 times differentiable, the rate of approximation is still 1 over n. So in other words, the Bernstein polynomial of f is unable to exploit additional smoothness. Sounds like a bad problem. It turns out we can circumvent both of these issues. So I won't talk about either in too much detail, but I'll just give you the bare essentials. So let's start with the sigma delta issue. How do we deal with high dimensionality for sigma delta? Well, so what is really the issue? So sigma delta requires some ordering, okay? Now, in let's say 2 dimensions where we have, let's say, a tensor product of Bernstein polynomials, how do we process them? What is the order? You could say I process left to right, then up, down. Perfectly reasonable and natural. You could say I go down, then right. You could look at other ways. You could look at like a snake-like Hamiltonian path. You could look at this other path as well. Which one's right? Which one do you pick? Well, it turns out by some miracle from magic of the Bernstein polynomials, this is the right one. We simply just scan in 1 dimension. We don't do anything more complicated or fancy. And when we scan in 1 dimension, we can still stay within the 1-bit world because 1 bit for 1-dimensional sigma delta, that's known. So if we just apply in 1 direction, we can still get away with 1 bit. Normally, this would be a terrible idea. For any other general types of sequences, functions, this would have almost no chance of working. But Bernstein really saves the day here. So the theorem is we pick an L, which will be the direction in which we process. And as long as we have an input sequence that's bounded by strictly less than 1, we'll pick the sigmas to be the solution to an rth order sigma delta scheme applied to the L direction. Schemes like this were really first studied by Ingrid Dobuchis and Ron DeVore in their Annals paper in 2003. So we're really relying on some powerful machinery here. That's fine. I mean, this is just a 1-dimensional scheme. We'll apply the 1D result, extend it to D dimensions, just doing it coordinate-wise at a time. Then, if we have this multivariate linear combination of if we have this linear combination of multivariate Bernstein polynomials, its error with respect to our plus and minus 1 sequence is again, well, we have some term where the boundary comes into play. But the point here is that the decay in n is like n to the minus r over 2, where r is the order of the scheme. Okay, so that solves one issue. Second issue is how to deal with this iterative Bernstein. Well, there's no point in doing all of this hard work for this extra decay in n if we're ultimately going to be penalized by this bottleneck decay of 1 over n, right? Well, this was also, thankfully for us, also studied in the literature. In the 70s, McKelly and Feldbecker, they were already aware of the saturation issue. So they looked at these iterative Bernstein operators, U subscript NM. And they were able to show that for every S times differentiable function, the error between F and a carefully chosen power of this iterated Bernstein of F does in fact take advantage of smoothness. The decay is on the order of n to the minus S over 2. Okay. So, I mean, this is already a very wonderful result, but this is for 1D. So we still have to extend this into higher dimensions. And the second issue is that we don't really want iterative Bernstein because when we do the quantization, it has to be presented to us in the form of a linear combination of Bernstein. So after this iterative Bernstein, we'll still have to convert it to a linear one. And well, we're able to do so, but there is an important aspect here. So the theorem says that for any dimension, for any smoothness, for any delta, for any CSF, as long as n is sufficiently large, we can approximate f with a linear combination of Bernstein. And this actually takes advantage of the smoothness. And the important yet subtle part here is that we're not achieving this approximation by blowing up the coefficients here. The coefficients are quite reasonable. They're just slightly larger than f. They're only delta bigger. So the relationship between delta and n is that delta is like 1 over n. So in other words, as we increase n, this delta is also decreasing. And really the key here is that it's not that Bernstein polynomials are bad at approximating smooth functions. It's really that the Bernstein polynomial of f is bad at approximating smooth functions. So the key here is that the a's are no longer f evaluated at k over n. They're chosen in some other way. Okay, so that's the approximation error. Let me now talk about how neural networks come into play. So another advantage of Bernstein is that they have a natural Pascal triangle interpretation of them. So as with a network, we always start with an input x. We can create new Bernstein polynomials simply by multiplying the previous ones by a certain weight. So for example, I start with x. I can make x by multiplying by 1 bit. I can create 1 minus x. This is still 1 bit. I'm only using 1 and negative 1. To make x squared, I multiply x by x. So x was already previously computed, but I need to now use multiplication. I'll talk about this in a second. But provided I have multiplication, I can make x squared. Next one, to make 2x times 1 minus x, I need to multiply x with 1 minus x. I can do that because 1 minus x is already made. If I have multiplication, this is fine. Then I multiply 1 minus x with x. Again, multiplication. But I can add them together, and this is fine. This is still 1 bit because I just need plus 1. I can continue to make 1 minus x squared. I multiply 1 minus x with 1 minus x. And then I continue. So notice that every subsequent row of this Pascal triangle, it can be made from the previous one together with multiplication by a polynomial of degree 1. And so as long as and all of this can be done 1 bit, as long as I can do multiplication. So how do I do multiplication? This is pretty well known in the approximation by neural networks community. Essentially, if I want to multiply a times b, I can rewrite ab as this sum. And this formula is helpful because you can see that as long as I know how to square a number, I can implement multiplication through this formula. And it's even better for us because for us, since we're using Bernstein, A and B are between 0 and 1. Okay, so if we use a quadratic nonlinearity, this is trivial, right? Like if rho is t squared over 2, then A times B is this thing in terms of B. And this is still 1 bit because to do A plus B, I just need plus 1. To do minus, I need minus 1. Another minus 1 here. A and B, their coefficients are 1, still 1 bit. So this is a 1-bit quantized quadratic network. We can also do this with ReLU if we want to. So this was really an idea introduced by Yarotsky. He really took advantage of this classical formula. And it allows you to say, okay, if I want x squared, I just have to truncate the sum. I'll have to pay up the price in some type of error. But thankfully, the error is not bad. And each of these phi's, this is the composition of phi with itself m times. Each of these phi's is one of these like tent or hat functions. But you can see that phi can be written, I mean, I don't have the formula here, but it's believable that phi can be written as a linear combination of ReLU terms. And each of these guys only needs plus minus 1, plus minus 2, plus minus 1/2. So using this idea of Yarotsky, but making some slight modifications, we can do approximate multiplication with plus minus with this like 3 bits quantized ReLU network. Once, like I said, once you have approximate multiplication or multiplication, implementation of the Bernstein polynomials is simple. We just follow this triangle. I mean, the analysis is a bit tedious because in the ReLU case, we'll make like some error every time we do a multiplication. But as long as we do the analysis carefully, it all works out. Okay, so we're ready to now state the final result. So like I said, the main strategy is this 3-term decomposition. But the key here is we'll use Bernstein or multivariate Bernstein polynomials as the basis functions. We have a bound on all 3 of these error terms, and we just put them together. So here's the final theorem. Fix any smoothness and dimension, any mu, S times differentiable F, infinity norm bounded by mu. So for any L, this will be the direction we apply sigma delta to. And for any integer n that's big enough, we can find a neural network that's implementable by a coarsely quantized neural network. And it satisfies this error rate. So as long as the Lth direction of x is far away enough from the endpoints, the decay rate in n is like n to the minus s over 2. So it does exploit the smoothness of f. And this neural network can, depending on which activation we want to use, but if we use the quadratic network, we can do this with 1 bit. And this is a much more elegant implementation. But I know like ReLU is more practical. People use ReLU more often. So we have this result for ReLU. It's not as nice. We need 3-bit. We can actually reduce this to 2-bit, but we really didn't find any point in doing that. But for 3-bit, you know, it has this many layers, nodes, and parameters. Okay. So the way the network works is for each coordinate of my variable, I first form the univariate Bernstein polynomials. I multiplied them together to find all the multivariate Bernstein polynomials. Now, in the quadratic case, these b's will just be the Bernstein polynomials, but in the ReLU case, the b's will be an approximation of the p's. And then this final layer performs the summation, where the final layer weights are only plus and minus 1. Okay, so really the final layer captures all the information about the function. Like this upper part is fixed. It doesn't depend on f at all. So in this sense, I feel like really counting the number of parameters for this upper network, I mean, it's a question that people are interested in, but I feel like it's not really an important question here because this part is really fixed. It's really all the magic comes from these plus and minus ones. And I like to think about this in terms of like image compression, like when you do like compress an image with Fourier wavelet, you just count the number of large coefficients. You don't count like how much does it cost to store the wavelets in memory, how much does it cost to re-implement the wavelets to synthesize, etc. So I really think of this as like the synthesis part, and then this is really the information part. So from that perspective, it's really this part that matters. But anyways, like I said, all of our results are constructive. So I can actually calculate these A's and the sigmas used in this approximation. And in fact, all you need to know are F at these lattice points. You give me F at these lattice points, I can calculate the A's and the sigmas, and there's this approximation guarantee down here. So to wrap things up, let me just describe some kind of a very natural open question. And of course, the question is, how special is Bernstein here? Can you adapt or generalize these techniques to other approximation systems, Fourier, wavelets, other approximation schemes like Legendre, Chebyshev, those types of things? And to be honest, I have no idea. Okay, this is kind of, we just finished this work, so we haven't had too much time to think about these other directions. But it does seem to me that Bernstein is very special. So a few important properties we use, so kind of probabilistic properties like Bernstein are non-negative, form partition of unity. We also have some good bounds on like their central moments. This we use quite often. But really kind of the main like analytical tools or the main like properties are that the Bernstein polynomials are localized to a certain degree. So if you just think about 1D, each Bernstein polynomial in L1 is on the order of 1 over n, which is, better than Fourier, but definitely much worse than, say, wavelets, right? But my feeling is that if the system is too well localized like wavelets, if you were to try applying sigma delta to wavelet coefficients, it probably wouldn't work. That's my feeling. But it's possible that a different type of algorithm could work for something like wavelets. Finally, we use the fact that they can't, like consecutive differences of Bernstein polynomials cancel out quite well. So there's, in that sense, even though the Bernstein polynomials form a basis, you can say that there is some redundancy, but it would have to be in a different sense than what people usually refer to in like frame theory. And then finally, because of our constructive algorithm, it's actually possible to give a binary encoding of any neural network. So if you give me a trained neural network, say like AlexNet, I can query the network at lattice points, right? Because, I have the trained network. I just tell the network, okay, what is the output at each of these lattice points? And then once I know the value at each of these lattice points, I can use this algorithm to now produce a stream of 1-bit coefficients. I mean, these are done in 1D, so they could even be computed in parallel if one wanted to. But the stream of plus and minus ones are really a binary encoding of this network. So I don't know. I mean, this could be a crazy idea. Who knows what will happen if one were to do this, but it's something I would like to try. Okay, and so for those who came a bit late, I want to reemphasize that all of this was joint work with Sinan. And if you are interested, you can find the 2 papers that this talk is based off, either on the archive or on my website. So thank you so much for your attention. It was really an honor speaking.